All right, what's up, guys? This is the question number 2 from the 2013 BC exam. In this one, you're given two polar curves, r equals 3, which is just a circle, and r equals 4 minus 2 sine theta, which is this blue graph right here. Okay, the picture's drawn for you on the question, and you're told that those polar graphs intersect at pi over 6 and 5 pi over 6. And in part A, you're told to find the area of the shaded region, which is S. So the shaded region is this orange stuff in here. Now you should be able to tell that like this half over here has the same area as this half over here. So when I do my integration, I'm going to account for that by just multiplying my integrals by 2. All right. So if you look at this, when you integrate polar, just remember like it's this plus this plus this plus this. It's like you're taking lines out from the origin, like this radian plus this radian plus this radian plus this radian, etc. Okay, now the way this guy's set up, I think it's going to be easier to find this half over here and then just double it to get the entire shaded region. Okay, so it's like if I start here at pi over 2, and I run into the blue, I run into the blue, I run into the blue, I run into the blue. Like I'm running into the blue graph from pi over 2 all the way to 5 pi over 6, all right? So I'm gonna like have that as my integration for that piece of it. So 1/2 times the integration from pi over 2 to 5 pi over 6, so that funky curve squared, d theta, and then I'm multiplying it by 2, right? Because I'm getting both this and this at the same time by just timesing it by 2, all right? And then to that, I'm gonna add, well, it stops running into the blue graph and starts running into the purple graph, okay? And that happens from 5 pi over 6 to 3 pi over 2. So I'm gonna say, all right, plus the integration of 1/2 from 5 pi over 6 to 3 pi over 2 of that radius squared. And then again, I'm timesing it by 2, right? Because not only will that give me this part, it'll also give me this part over here, okay? Remember that your integration feature is in Math 9, so you just push Math 9 and start doing it. You do not need to change your calculator to polar. Just pretend like those thetas are x's, and you should be fine. Just be careful with your parentheses, okay? Part B, it says that there's a particle on this polar curve right here. It says that your thetas are supposed to equal t squareds, and it wants the x coordinate of the particle's position to be -1. Okay, so we know that x equals r cos theta. All right, so that's just replacing rn for what it is. Then it said theta was t squared, so x equals, it's the exact same stuff with t squared it's being replaced in. And it's asking us to find when the x coordinate's position is -1. Well, this is like the x coordinate is that thing right there. So its position is -1 when x is -1. So -1 equals that stuff right there. Now, in my opinion, it's easier just to go ahead and make that guy equal to 0. So that way you're looking to see where the graph crosses the x-axis, okay? Because your output is 0 at the x-axis, all right? Now, I know this stuff says x equals stuff with t, but you got to think about it like output equals stuff with input. Output equals stuff with input. So without changing our calculator mode at all, we're just going to go to y1 and say y1 equals this stuff right here. Now, again, I'm going to pretend like those t's are x's. No big deal. It's fine. And then I'm going to graph this thing right here. Okay? And when you do, I would set your window. Like I think the problem says the particles or the time is between 1 and 2. So I'm setting my x min at 1 and my x max at 2 and my x scale at 1. And then I'm looking for when this thing crosses the x-axis, like when the output value is 0. And so to kind of zoom in on just the thin strip that is the x-axis, I make my y min be -1 and my y max be +1. My y scale can stay 1, that's fine. And then further on down the window, you can see there's an x-res feature. I make that 2, it just makes your graph appear faster, okay? So, and all of that stuff is located in the window feature. So just hit window and then change your window values to what I just told you to, okay? So when you graph it, all right, you should get something that's like that, all right? And so you're looking for that guy right there. So your 0 feature for that is second trace, and then choice 2 says 0, and then you've got left bound, so cursor over somewhere in that neighborhood, and then right bound, cursor to somewhere there, and then enter through your guesses, and you should get t equals 1.428 out, okay? And then part C, it says find the velocity vector for that polar curve, and again, you're replacing your theta value with t squareds. Well, your velocity is going to have both movement in the x direction and in the y direction. So you're going to have an equation for both x in terms of t and for y in terms of t. Well, we already know that x of t is equal to this. We did it in part B, okay? And so this is like x's position, okay? If I want to know x's velocity, it's just the derivative of that. So basically x prime of 1.5. So from your home screen, you can hit Math 8 and then type that in and then evaluate it at 1.5. And again, it's fine. Like your t's, you're just pretending like they're x's for putting it in your calculator. Not a big deal, all right? And then you also need the velocity piece in the y direction. So y of t equals r sine theta. So, and the thetas are t squareds, again, fine. So we need to know this is like y's position. So his velocity would be the derivative of that. So Math 8, type that stuff in, evaluate it at 1.5, out pops negative 1.672. Okay, so then the velocity vector, the way that you notate it, is like with those little, alligator mouth looking things. That's just what a vector looks like in calculus class. So there's the movement in the x direction, there's the movement in the y direction. All right.